talk before lunch break. Great, thanks, Jelani. All right, great. Thanks for having me. So this is work on sublinear time algorithms for approximating eigenvalues. It's joint work with my student Rajarshi Bhattacharjee and Archana Ray, and then Petros Trineas and his student Gregory Dexter. And it appeared at iCalc. So what's the problem here? It's one of the sort of most simple problems in linear algebra. We're given a symmetric matrix A, and we want to compute approximations to all of A's eigenvalues. It's symmetric, so A has n real eigenvalues. It's an n by n matrix. We know that we can do this nearly exactly, or basically to extremely high precision, in roughly n to the omega time with a full eigen decomposition or full other matrix decompositions. But this is prohibitively expensive for large n. So if n is really large, even something like n squared can be expensive. We also know that we can get really accurate approximation of the eigenvalues using iterative methods that basically repeatedly multiply your matrix via vectors. This is kind of like the methods that David talked about yesterday, like matrix vector query algorithms. And very roughly speaking, I'm not going to go into the details on these types of methods, but basically, if I want to compute k eigenvalues, like the largest k eigenvalues or the smallest k eigenvalues, it takes roughly k matrix vector multiplications. So if A was like a dense matrix, it would take like n squared times k time, very roughly speaking. In practice, these are the algorithms that are used to compute large-scale eigenvalue problems. So iterative methods, like if you wanted to compute eigenvalues of large matrix in Python or really any language, they would use these methods. The question we're asking is, what if I don't want to pay n squared time? I want to go faster than that. And in particular, we're basically asking, can we approximate the eigenvalue spectrum in sublinear time? So if the matrix is dense, which I'll just assume throughout this talk, just so I'm not talking about like NNZA or something, just n squared is my baseline time to read my matrix. I want to run in like little o of n squared time and still get non-trivial approximations of the eigenvalues. Okay. So what I'm going to show today, the result that I'm presenting, is basically a really simple sublinear time algorithm that approximates all the eigenvalues of a symmetric matrix A up to some additive error. I'll explain sort of the meaning of this error later, but it's basically scales as some error parameter epsilon, the size of the matrix n, and then the largest magnitude entry in that matrix, using polylog n over polylog n and 1 over epsilon samples. The algorithm's trivial. I'm just going to take my big matrix. I'm going to sample a smaller principal submatrix from that randomly, and I'm going to compute the eigenvalues of the smaller principal submatrix and use them to approximate my original eigenvalues. So the algorithm's trivial. The main work is analyzing, why does this give me good approximations? We're going to show some improved results. Basically, you can get like less coarse error bounds if you have some more information about your matrix. So if you can sample rows or columns with probability proportional to either their norms or their sparsities, which in many settings you would have access to this type of sampling. And then I'll mention some open questions on some linear time algorithms for eigenvalue approximation and how they connect to things like what David talked about yesterday, like query optimal linear sketching algorithms for eigenvalue approximation. Okay, so our main result, stated slightly more formally, is I have a symmetric matrix A. Throughout this talk, I'm just going to assume that I scaled A so that its largest magnitude entry is bounded by 1. Everything holds in general, but I just don't want to have to keep writing A infinity, so just assume the largest entry of the matrix is bounded by 1. What we show is that there's an algorithm that reads log cubed n divided by epsilon to the 5th entries of this matrix and outputs a set of n eigenvalues such that for any eigenvalue of my original matrix, my approximate eigenvalue is within epsilon n of the true eigenvalue. Actually, I guess any questions on just the problem or the approximation guarantee?
For a random matrix, the eigenvalues would be of order squared n, right?
Yeah. I'll talk in a bit about when is this approximation guarantee non-trivial. If you have a random matrix, the eigenvalues will roughly be square root of n, so it could just output all zeros. So we're really trying to detect like large eigenvalues. This really will be able to detect any large eigenvalues. So for example, if I have a matrix which is like, let's say I have a random matrix, but it's like a gram matrix of a low-dimensional random matrix, the eigenvalues of this matrix will scale with n. And so I'll be able to approximate the eigenvalues of that, but not of some general random matrix. Yeah, so let me talk about this related to Nikhil's question. How good is plus minus epsilon approximation to eigenvalues? Is it a good bound or is it trivial? One thing you can note is that all the eigenvalues of your matrix are always bounded by its Frobenius norm. And if I've scaled the entries to be bounded by 1, they're all bounded by n, right? So my approximation error is epsilon n. So it's at least on order of kind of the largest these eigenvalues could be. If I want to look a little bit more carefully at it, the sum of squared eigenvalues is equal to the squared Frobenius norm, which in my setting will be bounded by n squared. So what this means is that there's at most 1 over epsilon squared big eigenvalues. Basically, there's at most 1 over epsilon squared eigenvalues that are actually bigger than epsilon n for any epsilon. So what this means is that I only give non-trivial approximation to those eigenvalues. So even though I have this like L infinity guarantee on approximating all the eigenvalues, it's really only meaningful for the top 1 over epsilon squared eigenvalues. And this is maybe not super surprising. My algorithm's really fast. It's only running in poly 1 over epsilon time. There's no way I'm going to be able to approximate like actually all the eigenvalues. So really, I'm getting up good approximations to any big eigenvalues of the matrix. And it's easy to see that this is basically optimal. So we don't know the optimal epsilon dependencies, but you definitely need additive error scaling at least linearly in n times the infinity norm of the matrix. You just can't avoid this. I mean, one reason you can see why you definitely need to scale in the infinity norm is I could have a matrix which just has like 2 insanely large entries, right? If I'm sampling my matrix in sublinear time, I'm never going to find those entries. So I don't know, and everything else is zeros, let's say. So I don't know whether my eigenvalue is 0 or whether it's some massive value that's determined by those 2 entries. So if you definitely have error that needs to scale on basically the size of the entries of your matrix. And it's not hard to show that you also have to scale linearly. Actually, I think I'll show that next. So any questions on this? Oh, yeah?
Are you just assuming symmetric or also PSD?
I'm assuming symmetric. We can get tighter results for PSD, but I'm not really going to talk about it. Yeah. So actually, if it was PSD, there would only be 1 over epsilon outlying eigenvalues. You can check, and this makes things a little bit easier. Okay, cool. So here's the lower bound instance, which basically says that if I want to get additive error epsilon n, I definitely need to read like 1 over epsilon squared entries. So this kind of tells me if I'm just reading poly 1 over epsilon entries, then I definitely have error scaling in n. So the instance is simple. I either have an identity matrix whose top eigenvalue is, all of its eigenvalues are 1, or I have this block matrix where it's basically the identity with a big-ish block of 1s. So that's an epsilon n by epsilon n block of 1s. I've drawn it in the top left corner, but say I like permute the rows and columns of the matrix, which doesn't change the eigenvalues, but it hides these 1s, right? So they're scattered throughout the matrix. The top eigenvalue of this matrix is large. It's epsilon n plus 1, because or actually it's probably just epsilon n. I don't think there's a plus 1. But anyways, it has a big eigenvalue. If I read less than 1 over epsilon squared entries and I've scattered these 1s throughout the matrix, with high probability, I'll never see a 1. I'm only going to read zeros. So I'm never going to be able to tell apart these 2 matrices. So basically, we know that if I want error like epsilon n in my eigenvalue approximation, I need to read at least 1 over epsilon squared. So this is kind of the hard case why we have to scale. Okay. So what's our algorithm that's going to achieve our error guarantees? It's a trivial algorithm. We're basically going to just take A, our big matrix. We're going to sample a random principal submatrix. So sample a set of rows, sample the same set of columns, look at the intersection, you get a random principal submatrix. The rows and columns are sampled uniformly at random. And then we're going to compute the eigenvalues of this small matrix and use them to approximate the eigenvalues of the big matrix. So it's a very natural algorithm. The sample size S is going to be polylog n over epsilon. This is going to be where our eventual sample complexity comes from. And we're just going to basically include each row or column independently with probability S over n. We're then going to scale up this matrix by a factor of n over s to kind of keep expectations correct, right? If I just subsampled my matrix, then all the eigenvalues are going to proportionally scale down. So I'm scaling up by the inverse of my sampling factor. And then I'm going to use those eigenvalues to approximate the eigenvalues of A. That's the algorithm. One question here is like, AS only has roughly S eigenvalues because it's roughly S by S, right? whereas A has n eigenvalues. So I'll tell you in a second, how do I get like align these eigenvalues? It's very simple though. And then the other thing I wanted to mention, but I'm not going to talk about it in this talk, is our actually like the best result that I showed a few slides ago. We do a further pre-processing step where we kind of like randomly what we do is we literally randomly entry-wise sparsify this matrix. And using like known bounds on entry-wise sparsification, we argue that this preserves the eigenvalues and it saves us a little bit in the sample complexity. But it's just an optimization to get better bounds, so I'm not going to talk about it in this talk. I also think like if our analysis was tight for the first step, we wouldn't need to do this. Okay. Any questions about the algorithm? Yeah.
Is it clear it's better to pick a submatrix and sample within it than like sample a bunch of things all over and look at that?
It's not clear. It's a really good question. So the lower bound is what I showed a slide ago, is 1 over epsilon squared. And we're pretty far off of that. We're getting, the best we get is 1 over epsilon to the 5th. It's a great question to try to match it. I have no real idea how you would basically sample like somehow 1 over epsilon squared entries throughout your matrix, which is basically like no entries. It's very sparse. I don't know how you would then figure out eigenvalue approximations from them. So I think it's an interesting question because there might be like a totally different algorithmic approach that we haven't hit upon yet. So this is one question I think would be fun to work on.
Thanks.
Other questions here? Okay, cool. Just to give you a sense of exactly how the approximation works, I compute the eigenvalues of this small matrix AS. I get a list of not very many eigenvalues. And then to align them to the eigenvalues of A, I need to approximate n eigenvalues. I just like take the positive ones, put them on the positive side, take negative ones, put them on the negative side, and then anything else I fill in with zeros. And this is just matching the fact that I'm only expecting to approximate the large eigenvalues anyways, right? So the large eigenvalues of AS, positive or negative, approximate the large eigenvalues of A, and everything in between is small, so I can just trivially approximate it by 0. Okay. So this is my actual like list of approximate eigenvalues. Okay. Before I go into like sort of how we prove this, I just want to mention some other bounds that we have when we have better sampling routines. So here I'm getting in the, so consider, for example, I'm still in the same setting. I have a symmetric matrix A. Its entries are bounded by 1. But now maybe it's not dense and it has n and ZA non-zero entries, which maybe is a lot less than n, right? Think about like a sparse adjacency matrix of a graph. Typically, n and ZA is way, way, way less than n squared. Let's say I can also, n and ZAI is the number of entries in row I. And let's say that I can sample an index I proportional to n and z of AI. This is pretty simple to do. If you've stored your matrix in sparse matrix format, one thing you can do is just sample a random entry of the matrix, and it will land in row I with probability n and ZAI divided by n and ZA. So if I have sparse matrix format, this is kind of free to be able to do this. Okay. So if we can do this, if we can sample with probability proportional to sparsity, we get an algorithm that has also polylog n over epsilon sample complexity. Note that my polys are way worse here. But I get a much better error guarantee. My error scales as epsilon times square root of n and ZA. And like, what's the meaning of that error guarantee? Well, the eigenvalues, remember, are bounded by the Frobenius norm, which is bounded by square root of n and ZA if my entries are bounded by 1. But this is always less than n. And if n and ZA is much, much smaller than n, then this will be way, way less. I mean, if this is much less than n squared, then this will be much less than n. So this gives a much better error guarantee than our dense algorithm, right? So if you're in a sparse graph and you're thinking about n and ZA as scaling linearly in n, the error becomes square root of n rather than n. Okay. As I mentioned, you can do this type of sparsity sampling really efficiently. It's also very related to like adjacency list queries in the standard like sublinear time graph algorithms literature. So these type of queries are fairly reasonable to assume. Yeah. And then one thing I wanted to mention here, I don't know if I'm going to get to talk about this result much, but surprisingly, our algorithm here is not super simple. What we do is we basically sample this random principal submatrix AS, but we can provably show that the eigenvalues of AS are not good approximations to the eigenvalues of A. We have to do this weird step where we basically carefully zero out certain entries of the sampled matrix that got scaled too much in order to make sure that our eigenvalue approximation is concentrated. So this algorithm is a little bit complicated, And that's reflected in this very bad sample complexity, like why we have a to the 16 power. So I think one interesting question here is basically like, what's the right algorithm here that we could then get towards a tight bound? Okay, any questions on that result? Yeah.
That extra zeroing out that's only necessary in this sparse case?
Yeah, it's not necessarily in the uniform case. I think I'll have time to explain where this comes from, and if not, I can talk about it offline. It's actually also necessary in the next case I'll discuss, which I'm just going to go over really quickly. You can also assume an even stronger sampling oracle where I can sample rows and columns proportional to their squared Euclidean norm. If I can do this, I get a similar result, but my error gets even better. Now it scales with the Frobenius norm of the matrix. So again, just as a comparison, the eigenvalues are always less than the Frobenius norm, which is less than square root of n and ZA, which is less than n. So this is kind of like the stronger form of sampling, and I get epsilon times the Frobenius norm. And if you're in David's talk yesterday, this is the type of guarantee that sketching methods give. But sketching methods aren't sublinear time. They have to like read the whole matrix, right? Of course, here I'm assuming this stronger sampling oracle, right? This type of sampling oracle has been studied for a long time in the randomized linear algebra literature. Like some of the early work on low rank approximation assumed this type of oracle, and they gave results that looked a lot like this with additive error epsilon times the Frobenius norm. But recently it's received actually a lot of attention in the literature on like quantum inspired algorithms, because basically Tang made this realization that a lot of sublinear time quantum algorithms, if you sort of compare them head to head with classical algorithms, if you allow the same type of pre-processing or the same type of data structures to be used, you actually should be able to assume that you have access to this oracle. And then she and many other co-authors showed that if you have access to this oracle, you can kind of dequantize a lot of these quantum linear algebra results. So this is one way to sort of view this type of result. There has been work on basically exactly the same problem, singular value approximation rather than eigenvalue approximation, which gives the same type of additive error guarantee with the same type of runtime, but using a quantum algorithm. So you could think about this as like a quantum, I mean, I'm not thinking about it that way, but it fits into the quantum inspired literature in that way. And in this result, by the way, we also get the messy polyfactors, and this is also because we have to do this zeroing out thing. Yeah.
Just quickly, so sampling model here. So the sampling model here is that first you get to sample a row proportional to norm square, and then you don't know the locations of non-zeros?
Yeah, you don't need to know the locations. Well, actually, sorry, in the quantum inspired model, typically what you can do, because you can build a fast data structure for something where I sample a row proportional to its norm, and then I sample entries within the row proportional to their size. That's typically what's assumed. We're not using the full power of that model. We just sample independently S rows with probability proportional to their norm, and then we form the principal submatrix from those rows. So we don't ever do entry-wise sampling. That's the same in the sparsity case as well, by the way. Okay, cool. Other questions?
Is there any reason to believe that it would be useful in this framework to sample several submatrices and perform the same?
Yeah, this is a great question. So there's prior work that I haven't gotten to yet, but there's prior work that solves a weaker variant of this problem, where they're just trying, actually David again mentioned it yesterday, where you're just trying to detect the presence of a large negative eigenvalue. And to get tight results there, they actually do sample multiple principal submatrices and sort of like aggregate the results. We don't know how to do that for our problem, but it's definitely something you could consider doing. Yeah, it's a great question.
Okay, thank you.
Okay, cool. Let me mention some related work before I try to like briefly sketch the proof techniques. There's been several works that study sort of sublinear time property testing algorithms for matrices in this bounded entry model where you're assuming the L infinity norm is bounded. So Balkan, Lee, Woodruff, and Zhang gave algorithms for doing things like testing rank, stable rank, matrix norms. And then the most closely related to work to ours, which is what I was just mentioning with these principal submatrices, was this really nice work by Bakshi, Chepurko, and Jayaram, which appeared in FOCS 20. And they basically gave similar complexity to ours, like O tilde 1 over epsilon, poly epsilon algorithms to test if A is either positive semi-definite or has one large negative eigenvalue. So in comparison to that work, our result is stronger in the sense that we approximate all the eigenvalues. So once you have the approximation of all the eigenvalues, you can trivially just check whether one of them was very negative or not. But their result has better epsilon dependence, and they actually get rid of the log n dependence entirely. So they have tight bounds for their problem, whereas we don't have tight bounds for our problem. So that's another gap that in our work that could be improved. And then I'll just mention that subsequent to our work, there's been this really nice line of work. There's these 2 papers by Nadell, Swatworth, and Woodruff, who basically give optimal eigenvalue approximation algorithms in the matrix vector query model, which is in some sense a very different query model because you're multiplying your matrix by a vector. You need to access all of its entries. It's very much not sublinear time, but the techniques look really similar. And I think that maybe like to get optimal bounds in our model, maybe some tools from what they're doing could be used. And I'll also mention that this was studied a while ago by Andoni and Nguyen, who gave some weaker guarantees, but also studied eigenvalue approximation in streams using basically linear sketching. Okay. And then finally, I'll just mention that there's several other works recently that look at spectral density estimation for certain types of adjacency matrices of graphs, like normalized graph adjacency matrices. Here, you basically, the spectral density you view as a distribution, placing point mass 1 over n at each eigenvalue, and you want to approximate this in like the Wasserstein distance. So there's this really cool work that actually gives a runtime which is independent of n. It's like 2 to the 1 over epsilon, using this sort of like random walk based. You basically run a bunch of random walks and aggregate them to approximate your spectral density. There's work by Braverman, Krishnan, and Chris Musco, who give like an n over poly epsilon time algorithm. So it's better epsilon dependence, but worse n dependence. Our result is really related to that. Like we can easily convert our guarantee to giving a guarantee in the Wasserstein distance. So we get epsilon n approximation in the Wasserstein distance. But they're sort of incomparable regimes because the eigenvalues of a general matrix with entries bounded by 1 lie in the range negative n to n. And this is kind of intuitively why we have this scaling with n. The eigenvalues of a normalized adjacency matrix, even though its entries can are bounded in value by 1, they lie between -1 and 1. So in their work, they get a much tighter bound, like scaling with epsilon. So it's just worth noting that like it's very related, but they're 2 separate regimes. They have a lot more structure to work with, and it tells them a lot more about their eigenvalues. Okay, and then just like the broader research goal that I've been trying to pursue for several years, and a lot of other people are working on, is using randomness to give sublinear time algorithms for natural linear algebraic problems, typically under some assumptions on matrix structure. So there's been all sorts of work on algorithms for positive semi-definite matrices or distance matrices, kernel matrices, these quantum-inspired algorithms. There's all sorts of work here that's related, done by a lot of people in this room. Often these get stronger bounds, but they assume some structure, whereas in our problem, we're just assuming that the matrix is symmetric. We essentially have no other structure.
Sorry, I think I missed something in the implication for Wasserstein distance. I thought your algorithms were saying that anything basically smaller than epsilon n, you could freely give 0.
Yeah.
Isn't that epsilon n squared Wasserstein distance?
Yeah, so if you added up our guarantee, our total L infinity norm is like epsilon n squared. But then
because
in
of the
Wasserstein
scaling,
distance, you have 1 over n probability at each eigenvalue, so divide by n, so it just becomes epsilon n.
Oh, I see. So okay, and it's still the same. Okay, thank you.
Yeah, and then they have that same exact metric, but they get epsilon instead of epsilon n, which is obviously way stronger. Yeah.
Oh, I see. And
Yeah.
so you're taking into account that the interval is
Yes.
scaled by.
Yeah,
Okay,
yeah.
thank you. Thanks.
Okay, other questions? All right, cool. So with that, that's kind of the context. That's the results. I'll go like briefly into the proof approach. I have till 12:30, right? Okay. Okay, so just recall, we're going to have a uniformly random principal submatrix. We want to show that if I scale that matrix appropriately, then the eigenvalues of this, appropriately padded with zeros, approximate the eigenvalues of the original matrix. And we want to show that the sample size can be polylog n 1 over epsilon. I'm going to get worse polynomial factors in the talk than I do in the paper because the ideas are the same. I'm not going to optimize them. The key idea is simple. It's appeared in a lot of literature in this area. I basically split my spectrum into a head and a tail component. So I split A into its outlying eigenvalues, which are basically bigger than epsilon n. These are the ones that we expect to get non-trivial approximations to. And then its middle eigenvalues, which are less than epsilon n, and like we're not going to get non-trivial approximations to them. Okay. So formally, I like look at the eigen decomposition of A. I let like VO be the outer eigenvectors and VM be the middle eigenvectors, and lambda O and lambda M be the diagonal matrices containing the outer and the middle eigenvalues. And then I can write A in this way. So I can write A as basically A projected onto its large eigendirections plus A projected onto its small eigendirections. Okay. Similarly, I can write my principal submatrix as the sum of two principal submatrices, the corresponding principal submatrix of my projection onto the outer eigendirections plus the submatrix on the projection onto the inner eigendirection. And so I'm going to analyze it in this way by just thinking about these two different components separately. Okay. So far I've written A as AO plus AM, large eigenvalues plus small eigenvalues, and S transpose AS, which is my principal submatrix. I should say S is just a way of writing sampling in a linear algebraic way. It's just a sampling operator that reduces the number of rows and columns. So I'm writing S transpose AS as S transpose A0, S plus S transpose AMS. My first step is I'm going to show that the non-zero eigenvalues of S transpose A0S approximate those of A0 to small error. Basically, I preserve the outer eigenvalues. This is going to be the most interesting step of the proof. My second step is going to be to show that the eigenvalues of S transpose AMS are pretty small in magnitude, like less than epsilon n. Basically, I don't care that I'm getting good approximation of these eigenvalues. I just don't want them to blow up and look like fake large eigenvalues. I want them to stay small. So I'm going to show that after sampling this matrix, I don't blow up any of the small eigenvalues. They stay small. And then I'm just going to combine these via like an eigenvalue perturbation bound, like via Weil's inequality. So if I know that I approximated the large eigenvalues to small error, and I know that the small eigenvalues remain small, then via basically a triangle inequality, or Weil's inequality as you call it for eigenvalues, we know that we approximated all the eigenvalues to like roughly epsilon. Okay. So these are really the two steps that I need to complete. Okay, step one. How do I approximate the large eigenvalues? I really like the proof idea here, and it's not our proof idea. It's from this Bakshi, Chepurko, Jayaram paper. The idea is that since I've assumed that my matrix has bounded entries, all of its outlying eigenvalues, like any big eigenvalue, correspond to basically an incoherent eigenvector, which means that all the eigenvectors that witness large eigenvalues are like well-spread vectors. They're not sparse. They place mass at a lot of different entries. And thus, they're pretty easy to approximate via just uniform random sampling. So this is not super hard to prove. So let's take any unit norm eigenvector. I know that A times V is equal to lambda times V. That's what it means to be an eigenvector. And I also know that lambda is big. It's at least epsilon n in magnitude, right? What this means is that the ith entry of V is like 1 over lambda times the ith entry of AV, right? Because I just divided by lambda on each side. The ith entry of AV is just the inner product between the ith row of A and the vector V, which by Cauchy-Schwarz is bounded by the norm of that row times the norm of V, right? This is at most root n, because I've assumed my entries are all bounded by 1. So I have an n-length vector, its norm is at most root n, and then V is a unit vector, right? And then this here is at least epsilon n, because I assumed it's an outlying eigenvector. So now I know that the magnitude of the ith entry of V is at most 1 over epsilon times root n. So what this means intuitively is that V is within like a 1 over epsilon factor of being perfectly flat. If its entries were all 1 over root n in magnitude, it would be perfectly flat. We have this 1 over epsilon slop, but pretty much it's almost a perfectly flat vector. I should be able to approximate it really well via uniform sampling. So any questions on this proof? It's pretty simple, I mean, or it's very simple, I guess. So this proof is an important part of this work by Bakshi et al. On testing PSDness. We kind of extend this to a stronger bound, which I'm not going to show today. We basically show that not only are the eigenvalue vectors entry-wise bounded, but in order to get a tighter result, we show that if I basically look at that whole outlying eigenvector matrix, all of the row norms of that are bounded. These are also known as the leverage scores of that matrix. I like to work with leverage scores, so like I always focus on bounding these types of quantities. If we can bound these, we know that sampling uniformly from that matrix will give us good approximations. So we give a stronger bound, but it's the same exact idea as this bound. Okay. So far, we know that the outlying eigenspace of A is incoherent, meaning its mass is spread across the indices, and its leverage scores formally are bounded by roughly 1 over n, or 1 over epsilon squared. What this means is via like a standard matrix Bernstein bound, if we take 1 over epsilon to the 4th samples, eventually this will be 1 over epsilon cubed. But again, in the talk, I'm not worrying about getting tight bounds. Then with high probability, if I basically look at a sampled inner product, so V is an orthonormal matrix, right? So V transpose V is the identity. If I sample the rows of V uniformly at random, because they have bounded row norm, V transpose SS transpose V, so the sampled inner product, is going to be close to the identity with high probability via like a standard matrix Bernstein bound. We can then use this to argue that the non-zero eigenvalues of our principal submatrix are close to those of the original matrix. So intuitively speaking, our principal submatrix can be written as S transpose V0 lambda 0 V transpose S, right? That's almost an eigendecomposition because after sampling, V0S is almost orthogonal, right? So this is almost an eigendecomposition of this. And so these are almost the eigenvalues of this. So basically, our subsampled matrix, its eigenvalues are close to the original eigenvalues of the matrix. I'm not going through exactly how we do these bounds, but that's the intuition behind what happens. So that completes the hardest part of the proof, which is showing that the outlying eigenvalues are close to the true outlying eigenvalues. So questions on that part of it? And the key here there is just that if your entries are bounded, the eigenspace corresponding to large eigenvalues must be incoherent, meaning it must be easy to approximate via sampling. It's kind of like in matrix completion, like you always assume your eigenspace is incoherent, and you get sublinear type algorithms. And so this is just kind of a justification that if you have large enough eigenvalues and you have bounded entries, it must be incoherent, basically. Okay. It remains to show that the eigenvalues of the S transpose AMS are bounded in magnitude by epsilon n. There's sort of 2 steps here. Basically, the first thing we want to do is show that because of the incoherence of the outlying eigenspace, A0, like after I take A and I project it onto the outlying eigenspace, it might make the entries not be bounded by 1 anymore, which could kind of mess up my arguments, right? But we show that the entries are still bounded. So even after projection, the entries are bounded by like 1 over epsilon. And then via triangle inequality, this tells me that the entries of AM are still bounded by like 1 plus 1 over epsilon. So they're reasonably bounded. So basically, after projecting onto that eigenspace, I haven't messed up my entry-wise bound all that much. And then once I have that, I can just apply known spectral norm bounds for sampling random principal submatrices of bounded entry matrices. So there's like a bound by Rudelson-Verschainen. I think we use an actual citation by Trop, which is basically that if I have a bounded entry matrix and I sample a random principal submatrix, the eigenvalues can't be too large. This is the type of thing that they study a lot in sort of random matrix theory. So the key step here is just showing that AM actually has bounded entries. That follows from incoherence, and then we get this down. Okay. So that's the entire proof. Just as a recap, I split A into its outlying, this is very classic, like its head and tail eigenvalues, outlying and middle eigenvalues. I prove that the outlying eigendirections are incoherent, and thus I approximate them via uniform sampling, and I preserve the outlying eigenvectors. I then use that incoherence to argue that the inner eigendirections, after I project onto them, the matrix remains bounded, and when I sample it, the eigenvalues don't blow up. And then I combine everything basically via triangle inequality. Okay, any questions on that? And then I'll talk a little bit about non-uniform sampling and some open questions. Yeah.
Do you get anything about the eigenvectors of the gap, the outer eigenvalue of the gap?
You mean about trying to like approximate the eigenvectors?
Well, you get eigenvectors of this compression, right?
Yeah.
Anyway, can you say the residual when you lift that back to the original space is small?
Yeah. I don't know how to actually lift it back properly to the original space.
Well,
Like, Oh, what?
I was going to say, this submatrix is basically a compression, right?
Yeah.
You can use that rectangular matrix to lift that.
Oh, yeah, but then you would get a really sparse lifted eigenvector, right?
Yeah, it could have
Oh.
some residual.
Yeah, maybe. Do we expect it would? I have to think about that. I kind of think I wouldn't expect it would actually have a small residual after lifting it, but it's a great question. We should look at that. Yeah. Yeah. So in theory, like you could, if you had an eigenvector of this matrix, you could then like call it X. You could then look at SX and say like, is this a reasonable eigenvector of the original matrix? Certainly, it's not a large eigenvector because it's sparse, and we know all the large eigenvectors are dense. But you could still ask like, what are the properties of this? I don't necessarily expect it to have small residual.
Okay.
Yeah, in the sketching methods, like where this is a Gaussian matrix, you probably can do some lifting like this. Other questions on this? Yeah.
So you suspected. So you said that you suspected that the zeroing out argument does not need to be done if there's something sharpened here. Do you have any sense of what part of this analysis is the part that would need to be sharpened?
Oh, I'll get there. I haven't
Okay.
actually, the analysis I just did, there is no zeroing out. I just take the principal submatrix and compute its eigenvectors.
Yeah, but he said that the zeroing out is done in order to like get slightly better rates, but that you wouldn't
Yeah,
need to do
so
that
the
if
zeroing
something-
out is done when I do non-uniform sampling. I'll talk about that in a second.
Okay.
And that's where we lose a lot of epsilon factors.
Gotcha,
The
gotcha.
bound we get here is 1 over epsilon cubed. And I'm almost sure the correct bound is 1 over epsilon squared. We've like simulated a lot, tried to find worst case matrices. This is what's known for linear sketches.
Mhm.
I don't really know how to shave that last epsilon. It's a little technical where it comes from, but basically like very intuitively, it doesn't come out in the proof I described, but the interactions between really big and really small eigenvectors can kind of mess you up and we lose an epsilon factor there. So it can probably be tightened, but I don't know how to do it.
Well, thank you.
All right, cool. So actually like that's a good segue into non-uniform sampling. I'm not going to prove these results at all. I'm just going to tell you in a minute why things get a little bit weird in the non-uniform sampling case. So we have a natural extension of our algorithm. I just sample each row or column with some probability pi, which is non-uniform. In this case, I'll consider the sparsity-based sampling. I take D to be a diagonal matrix, which appropriately rescales by like 1 over square root of the probability. And then I compute the eigenvalues of like D, A, S, D. So this is my submatrix appropriately rescaled, so it's correct in expectation. And then I just use these eigenvalues to approximate it. Okay. If my probabilities were uniform, this is exactly the same as my uniform sampling algorithm. So it's exactly just a generalization of that algorithm. Immediately, you can see that this algorithm completely fails when A is the identity. So if A is the identity, sparsity-based sampling is just uniform sampling. N and Z of A is N, right? So we need to approximate all the eigenvalues to error roughly like root N if we want to get our bound. But when I sample this principal submatrix, I'm just going to get an identity out, and I'm going to scale it by N over S. So the eigenvalues of my sample matrix are going to all be N over S. So if I want to get error root N, I would need to set S at least like root N. So I'm not going to get like a polylog dependence. So my algorithm just fails for the identity. It's like, okay, this algorithm just doesn't work. A simple fix here is you can zero out the diagonal of A. You can show that this doesn't affect the eigenvalues too much. And it resolves this one case. But you might suspect that this sounds like a Band-Aid, like it fixes the identity case, but there must be some other similar cases, right? And there are. So for example, consider this like almost identity matrix where you just have 2 bands of 1s, like right above and below the diagonal. Again, N and ZA is roughly N, so root N and ZA is roughly root N, and the eigenvalues are all constant. They're all less than 2. So I need to basically approximate the eigenvalues to error root N. And again, I'm roughly doing uniform sampling because pretty much every row and column here is N and Z, it has 2 non-zeros. So my matrix I get out is like N over S times my sample. If I take very few samples, then with good probability, my sampled matrix is just 0. I don't hit any of these 1s, right? And so we actually get good estimates. We get lucky in a way. But if I take a bit more samples, then by birthday paradox, with good probability, I hit one of these non-zero entries. And when I hit it, I scale it up a lot. And then the eigenvalues of my matrix are big. They're like basically like root n over c if I took c root n samples. And this is above my error guarantee. So this isn't necessarily a problem. Like you could just say don't take too many samples, but it kind of hints at a problem. I don't want an algorithm that as I start taking more samples, it starts failing. And there's lots of similar cases to this that will kind of destroy the algorithm. And yeah, so there's many related examples. Roughly what happens is if I have entries that are at the intersection of very sparse rows and columns, and I hit those entries by bad luck, I scale them up way too much when I sample, and it messes up my eigenvalues. So I'm not going to go into the details of how I deal with this, but I just wanted to point it out because it leads to an interesting open question. Basically, to handle these cases, we just zero out entries that are at the intersection of sparse rows and columns, and we ignore them when we sample. This ensures that none of them are scaled up too much, and we don't have any issues like I described on the last couple slides. And we prove that the zeroing out basically doesn't affect the eigenvalues too much, so it doesn't introduce too much error. So you can see the paper for the full argument, but the upshot is basically like we get a bound, which I'm happy with, but we lose tons of log n and 1 over epsilon factors. And I'm really not sure like what the right algorithm is here. Like if you had told me what's the right algorithm to estimate eigenvalues if you know the row and column norms, I would have said, yeah, sample the rows and columns with proportional to those norms and take the eigenvalues of the principal submatrix. It's surprising that algorithm fails. And I kind of wonder like what's the clean right algorithm that gets like tight bounds is kind of actually efficient. Okay, so I have like a couple minutes left. I'll just conclude with some open questions. Actually, wait, maybe I can take, are there any questions on the zeroing out stuff or the non-uniform sampling? Okay, cool. So I'll talk about some open questions. So our uniform sampling bound, we sample a 1 over epsilon cubed by 1 over epsilon cubed submatrix. We believe this can be tightened to 1 over epsilon squared based on simulations, and also just kind of, it looks like 1 over epsilon squared should be correct. That also would match what Bakshi et al. Get for PSD testing, which is a closely related problem. That would also match a lower bound for any algorithm that works by first sampling a principal submatrix and then doing some post-processing, right? So that would be tight for principal submatrix-based algorithms. It actually wouldn't be tight in general. The best lower bound, this is like 1 over epsilon to the 4th entries in total. The best lower bound we have for general algorithms is 1 over epsilon squared. So conceivably, there could be an entirely different class of algorithms that does even better. And I would be really interested to know like what that class would be. I'll also mention another evidence that this bound may be correct is that when A is PSD, there's a trivial proof based on approximate matrix multiplication that gets this bound and loses no log n factors or anything. So I didn't go through that, but that's another maybe evidence that we could tighten our bound in the general case. Okay, and then, okay, more evidence. I forgot. I kind of forgot the order of my slides. If I just care about the singular values, right? The singular values are the magnitudes of the eigenvalues. So approximating the singular values is kind of like approximating the eigenvalues, but where you lose the signs. Just via a very simple matrix Bernstein bound argument, if I independently sample some rows and some columns of A, I can prove that the singular values concentrate, and I just need 1 over epsilon squared samples. So I can actually approximate the singular values very easily with a trivial proof, but somehow getting these signs correct and the fact that we do like a principal submatrix, S transpose AS, makes things a lot more complicated. There's been recent work that David talked about yesterday that gets tight bounds in the sketching model where instead of looking at a sampling, they look at a bilinear sketch, G transpose AG. So maybe we can use some techniques there to tighten our bounds. Although something that's kind of annoying is that this result that David has only works for Gaussian sketching matrices, which is very rare. Usually when you prove sketching results, they work for like any sub-Gaussian sketching matrix or like even broader classes. It only works for Gaussian sketching matrices, which annoyingly means it doesn't like easily generalize to like, usually in my view, anything you can do with sketching eventually will figure out how to do it with sampling. But we're not able to do that here because this is a kind of a weird form of sketching where you really need Gaussianity and rotational invariance. Okay, and then, sorry, I'm out of time. There's other questions like, I mentioned this one already. Can we get tight sample complexity overall? What's even a plausible algorithm here? Can we do anything interesting in the case when we have small eigenvalues? So this is related to like Nikhil's question at the beginning. If I have a random matrix, all of its eigenvalues are roughly like root n. The sum of its absolute values of eigenvalues, which is called the Schatten-1 norm, is like n to the 3 halves roughly. Can we approximate that Schatten-1 norm to error even like 1/2 times epsilon to the 3/2, like anything non-trivial. Like, can I figure out whether I have a full rank random matrix or a random matrix with rank n/2? We have no idea. We have no lower bounds or upper bounds there. We know obviously you can read the whole matrix and do it. We have no lower bounds ruling out sublinear algorithms. So I think that's a really good question and would kind of get at this key challenge of how do we estimate like bulk spectral properties? Like, do I have a big tail of small eigenvalues or only a small tail of small eigenvalues? And then of course, like something I like to work on a lot and related to these graph adjacency matrices is if I assume further structure, can I get tighter bounds? All right, that's it. Sorry, I ran a little bit over. Yeah. Any questions for Cameron?
So is there any notion of like a different kind of information we could have about rows and columns? Like if you know the leverage scores of every row, is
Yeah.
there any hope you can do better there since leverage scores are already appearing in the analysis?
Yeah, one way you could view all of our algorithms is basically successively better approximations to the leverage scores. Like uniform is not so bad because we know the leverage scores are close to uniform. NNCA is a bit better. The row norm is a little bit better. If you actually knew the leverage scores of the outlying eigenspace, I think you could get 1/epsilon². I'd have to double check that. I'm not 100% sure. The problem is how are you going to learn those leverage scores? You don't know what that space is. But yeah, it's a good question.
Cool. Thank you.
Any more questions? If not, then let's look down once more.
The next talk starts at 2 p.m.